Hello world. Today we are tackling a fun and challenging problem, finding the minimum number of operations needed to move all balls into any given box. This is a common coding interview problem and that will really test your algorithmic thinking. So here's the setup. You're given a binary string where 1 represents a box containing a ball and 0 represents an empty box. Your goal is to calculate for every box the minimum number of moves to bring all the balls to that box. Sounds simple, right? Let's dive in. First, we'll look at the approach that comes to mind, that it is straightforward but not the most efficient. We calculate the distance of every ball from every box using a double loop. So here's how it works. So we are going to go through the range of all balls, let's say n. So here n would be the number of boxes that are present, and for all of these indices, that is for each of these box, we go through another loop, and this loop is for checking the distance to every other box. So every other box would be, if we have to check that if that box is 1 or 0. So if and only if that is 1, we will now move that particular ball to our index I. So we'll move the 1 from the box number j to box number I, and the number of operations needed for that would be equal to the absolute value of I minus j. So that is the, because we can only move a ball to an adjacent box, so whatever the distance is, we have to make that many number of operations. So simple, but this approach has a time complexity of big of n square, which isn't ideal for larger input. If you're processing 2000 boxes, this could slow down your program significantly. However, I just want to show you that this indeed would cause you problems. So let's just try coding out the rest of the code. So our answers, we need to return an answer array. So answer will be of the size n, and after I get the number of operations, I can populate answer I, which should be equal to the number of operations that were needed to bring all the ones to the ith box. That is what answer I will contain, and in the end I can return answer. And let's run our code to see if it works. So we need to also define our operations. So where should we define it? The best place to define it would be over here, because the number of operations would be different for every ball. And let's run that. Yep, it gets accepted that we do get our expected output and output to be the same. Now I'm expecting a time limit exceeded error if I try to submit it for really large values. So um, that's crazy. It actually got accepted. It was not what I was expecting. But here we are clearly doing duplicate work and we don't need to do so much. So the time, my runtime is 2700 milliseconds. Let's see if we can do better than that. So we are basically going to try and reduce the number of computations and bring it from a big of n square to a big of n solution. So here we can do an efficient two-pass solution. This solution calculates operations using two passes, one from left to right and another from right to left, achieving that big of n complexity. So you're only going through the full loop once. So instead of recalculating distances every single time, we sweep through the boxes twice, once from left to right and once from right to left. So here's the idea. In the first pass, we will accumulate the cost of moving balls from the left. So it looks as follows. So if I do a left to right pass, then from I need to go from the starting ball to the ending ball, and for all of these I'll add my number of moves to my answer, and after I do that I will update my count value. What is a count value? It is the number of ones I've seen so far from left to right, so that would be equal to boxes I. So if my boxes I contains a 1, then I'll add 1 to my count. If my boxes I contains a 0, then I'll add 0 to my count. Count represents how many ones I have seen so far, and the number of moves I need to make will essentially be equal to how many ones have I seen so far. So moves will be equal to whatever the moves was for the previous index plus the count. So what's happening here is, if my particular box is a 1, so when I go into the next iteration of the loop, I need to add the number of moves that I had to take to get to the previous one, and then I have to add one more move uh, that would be either 1 or 0. So count would be either 1 or 0, right? So if it is a 1, then I'll have to make an extra move to move all of the boxes. uh, this will be clear when we also make the right to left pass. So for I in range n minus 1 minus 1, so this is basically going from right to left. Here also the same thing, we'll update our answer variable with the number of moves that were needed to come to this position, and then we update our count variable, that how many ones we have seen from right to left. So that would be, are we supposed to add 1 or are we supposed to add 0 based on whatever the box's value is at ith position. And we'll update the number of moves required by count, like that. So this approach will let you go through the whole boxes array just one time. So the approach has a time complexity of big of n. So to recap, the knife solution works fine for small input but gets slower for larger input. On the other hand, the two-pass solution handles even the largest inputs efficiently. Both approaches produce the same results, but this is clearly better in terms of speed. Now let's try and test this if it works. So we need to define a few variables here. So I have my move variable which will be 0. I have my count variable which will also be 0. So this would be for left to right, and when I'm going from right to left I need to define it again or reset it to 0 and set count also equal to 0. And over here also I need my answer array, which will essentially be the size of the total number of boxes. So count 0 and count 0 essentially is the number of balls encountered so far, and moves is the accumulated moves, right? And in the end of it all we want to return our answer array, and let's check if it works. There we go, it works for the test cases. Let's check if our runtime improves from 2700 milliseconds. Look at that, it is the best solution possible and reaches 15 milliseconds of time. It is the best solution over here. So that's how you solve this problem with both the solutions. Let me know in the comments below if you want me to take a different approach to how I solve these problems. I essentially just look at them and try to think of a brute force solution and then try to optimize from there. But maybe the explanation would be clearer if I use diagrams. Let me know what you would feel would make me improve the solution. Till then, see you.